Alright, welcome to practice 2 for activity 5. In this video, instead of running a bivariate regression, we're going to add some more variables, or predictor variables specifically, and we will run a multiple regression. In this video, I also wanted to go over the different regression methods that we can use to create predictive models or our equations. We didn't really touch on this in the lecture, so I wanted to go over the mechanisms and kind of the concepts behind how each regression type or regression method adds or removes variables from the equation. So we're going to be using our practice 2 data, which basically is looking at batting averages, the percent of scores run, percent doubles, percent triples, percent home runs, and percent strikeouts. So we're pretty much looking at baseball stats. And in this particular example, and I'll note this in the activity so that it's a little bit clear, but in this one, batting average is going to be our dependent variable that we are trying to predict from using relationships with our predictor variables, which would be our stats, or our baseball stats. So the first task that you guys are going to do is run a multiple regression using the following methods. The first method we're going to do is the enter or hierarchical method, and we're going to insert strikes or percent strikeouts in block 1 and home runs in block 2. Now, the hierarchical method is used when the researcher has a good idea of the order that the variable should be inserted into the model. Now, the nice thing about this is that the researcher does have some degree of power because they get to choose the order that the variables go into, but the downside is that this method is reliant on the researcher knowing what they're doing. So if you assume that a variable is supposed to go into your model when it's maybe not the most appropriate variable, or maybe it is highly correlated with other variables, etc., 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 like a whole bunch of things could go wrong. If we don't catch those as a researcher, then hierarchical method isn't necessarily the best option. But I just wanted to show you guys what this looks like. Hierarchical method is defined by the researcher identifying the order of the variables that go into the regression. So in order for us to get started here, we have to highlight all of our data. So very similarly to our first spreadsheet, we're not doing a whole lot in or by means of manipulating information. I'm going to open up a new data set, and I'll go ahead and paste my variables in here. I can see all of my variables have been formatted. Again, if you have peace of mind by changing your measures to scale, by all means, please do it. But once we have our data formatted, all of our variables are parametric, we can go to Analyze, Regression, and Linear, same as last time. Our batting average is what we are trying to predict. And then in the instruction sheet, I noted you guys were going to put strikeouts in block 1, which we can see block 1 of 1. So we put strikeouts in our independent. And then we can say next. So that will tell our model or the regression to put strikeouts in the model first. And then we want home runs in block 2. So that'll tell it to put home runs in the second model that's generated. This will give us our enter method, right? So we keep that at default. For our statistics, we want confidence intervals, R-squared change since we're generating multiple models, our collinearity diagnostics, Durbin-Watson, and our case-wise diagnostics. And then we'll make the same standardized plots that we did in our bivariate regression example. Press OK, and we get our output, which looks something like this, right? So we can see that the variables entered in the first model we put in strikeouts, and then the second model we added home runs. Now, this is a great time for us to relabel our output. So instead of regression, oh no, what's happening? Instead of regression, I'm going to change the title in my output to be vertical jump in 100-meter time. Okay, that way I can distinguish which variables I've got operating where. I'll increase the size of that so that it stands out a little bit better. I think it actually should be 18. There we go. So this is what will actually populate into your spreadsheet when you convert this to a Excel file. That's what it's called. Small segue into editing your spreadsheets or editing your outputs. You can delete the logs because these take up unnecessary space. So the way you do that is you click on the icon and then right click and just choose cut. It'll take it out. You can do the same thing with the notes. I think everything else can stay there. Really, you can take out anything that we skipped over. So we didn't look at collinearity diagnostics and we didn't look at the residual statistics. So really, what you're including in your outputs are kind of what I would need to reference. So I'm going to take out notes. I'll take out the active data set. That doesn't really matter. No, we should be good to go from here. Okay, so I'll title this next regression. Come on. There it goes. Title this one. Jeez. I'll do batting averages, and this is my enter method, or you can put hierarchical method, just so you can identify which regression you're looking at. Now back on track, we saw our variables entered and removed. Okay, so now we know which variables are in which models. We then need to check our assumptions. So going through the output, we can see our Durbin-Watson value is between 1 and 3. So we'll say that we have independence of observations. Scrolling down, we can then look at our collinearity statistics, and we can see tolerance and VIF are for both variables. They're actually the same values for both models. They meet our assumption, so tolerance is in fact greater than 0.2 and VIF is less than 5, so that's a good thing. No multicollinearity in our data set. The excluded variables table, this is something that we didn't get to see in the bivariate regression. I'm just going to talk about it while we're here. Basically, this just tells you out of all the variables that we've inserted into our regression analysis, which ones were excluded for which models. So the coefficients table will tell you which variables were inserted into the model. The excluded variables will tell you which ones were not included in each model. So in this case, we only had two variables, strikeouts and home runs, right? So if home runs is not in model 1, it goes to the excluded variable section. That was kind of just a little extra tidbit. Again, we'll skip our collinearity diagnostics, so we'll get rid of that. There's a horrible lag in my SPSS. Okay, there we go. Residual statistics, again, if our case-wise diagnostics table doesn't come up, that means we probably don't have any outliers in our data, so we can get rid of that one. For our charts, we look at our histogram. Our mean is close to 0, right, with this little exponent of -15. And then our standard deviation is close to 1, which is good. Visually checking our histogram, our normal curve does relatively fit over our frequency distribution of our standardized residuals. So far, I would say that our residuals meet our assumption of normality. We can confirm this by looking at our normal PP plot, and the deviation from this line isn't that great. So I would say we also met our, or that we can confirm, double confirm, that our residuals are normally distributed. In our scatter plot, we can see that we've got our standardized predicted values plotted against our standardized residuals. For the most part, I would say that we have homoscedastic data. It is kind of looking like there's a little bit of a fanning effect going on. Kind of on this end of the distribution, you see how these residuals are further apart than the residuals are on this side. So in that case, I would say it's something we should be wary of, but it doesn't look so extreme that we should be concerned with it. Also, in our class, we don't go over any correction factors for violations to assumptions and regressions, just because there's so many assumptions to look at and you guys already have enough to remember. So I would say we have slight heteroscedasticity, but for the most part we're looking pretty good in the homoscedastic assumption. So while this might be a point of caution, I think we can still move forward with the analysis. Okay, so those are all of the assumptions that we needed to investigate in our output, which means we can go back up to the top of our output for this particular test. And then in your instructions, so we've gone through our assumptions for this particular model, and then we need to interpret the results of the regression analysis. So we can create a model equation from the model summary that we got, and then we can interpret the criteria for how the variables are entered or removed. This one we're not going to go super into for the enter method, because we know how we entered the variables, because we told the SPSS how to do it. Okay. And then the last thing we'll look at in this particular section is evaluating if the model is a good fit. So looking at various p-values. For our model summary, we can see that our R-squared, when we inserted strikeouts, was 0.386. And then now we can actually look at an R-squared change, right? So when we add home runs to our model, we increased our R-squared value by about 22%. So that raised us to a 60.5%, or 60.5% of our batting average is accounted for when we just look at strikeouts and home runs. Okay, and we could see that when we added home runs to our model, the change in R-squared was significant. Okay. Evaluating our ANOVA table, we can see that our last model, which is the one we want because we have both of our variables in here, okay, our p-value for our ANOVA is less than 0.001, which tells us that we significantly improved the prediction of batting average by using this particular regression model. Our coefficients in our B's, right, that's where we're going to build our regression equation. So similar to our previous example, we can say, let's just put an enter for our equation here. Or actually, let's do it this way. We'll put an equation, we'll have an equation column, and then we'll have an enter, a forward, and a backward, where we can insert our equations for the other examples. So in this one, we can do similarly to our previous example where we are saying that our y, or our batting averages, are equal to the constant of the final model, so 0.31. And then we do plus our b coefficient, so in this case I'm just going to put minus 0.499. That'll be multiplied by strikeouts, so I'm just going to put SO plus our next b coefficient, so 0.944, times home runs, which I'll just put HR. Okay, so remember that SO and HR are representing kind of placeholders for any given X value for strikeout or home run percentages. Okay, so that's my equation for my enter method. Cool stuff. All right, and then I think that's kind of where I want to stop on this one.